This morning, October 25th, 2025, at 7 Universal Time, the International Asteroid Warning Network, or IAWN, issued a bulletin, a notice most people would scroll right past without a second thought. Routine, they said. A scientific opportunity, they claimed. But here's what they didn't say in that carefully worded press release. Why planetary defense protocols, normally reserved for extinction-level threats, are being quietly activated for an object that supposedly poses zero danger to anyone. The campaign has a name, the 3I-Atlas Comet Astrometry Campaign, and it runs from November 27th, 2025 through January 27th, 2026. 2 full months of coordinated, round-the-clock observation involving observatories across 6 continents. Now, if you're not familiar with IAWN, let me explain what makes this unusual. The International Asteroid Warning Network exists for one reason: to detect, track, and coordinate responses to objects that might actually hit us. Asteroids on collision courses, comets with uncertain trajectories, things that could vaporize cities or trigger global winters. IAWN doesn't typically organize campaigns for objects passing safely in deep space. They've done exercises before, sure, practice runs, calibration tests, but those were announced as drills. This one? This one is being framed as a scientific observation campaign, yet it has all the operational signatures of an emergency mobilization. Astrometry, by the way, just means measuring where something is in the sky with extreme precision. You take multiple observations from different locations, calculate the orbit, refine the trajectory. Standard stuff for tracking near-Earth objects. What's not standard is the scale of coordination here. Universities, government observatories, amateur networks, all being asked to contribute data. Registration opened weeks ago. A workshop is scheduled. This is the kind of infrastructure you spin up when you need answers fast, and you need them verified by as many independent sources as possible. This is what you do when you cannot afford to be wrong. NASA's official statement landed about 6 hours after the IAWN bulletin. No threat to Earth. Those 4 words repeated in every interview, every press conference, every official channel. Dr. Lindley Johnson, NASA's planetary defense officer, went on record saying the object will pass at approximately 1.8 astronomical units from Earth. For reference, that's about 168 million kilometers. The Moon is only 384,000 kilometers away. So yeah, by cosmic standards, 3I-Atlas isn't even in our neighborhood. It's barely on our street. And yet, defense satellites have been retasked. According to sources who spoke to multiple outlets under conditions of anonymity, classified observation platforms operated by the United States Space Force and partner agencies have shifted their coverage windows. Deep space infrared sensors, high-gain radar arrays, assets that normally monitor geosynchronous orbits or track foreign satellites, are now pointed at a comet that officially poses no risk. One source described it as a precautionary reorientation. Another called it protocol compliance. A third, more bluntly, said it reminded them of the scramble before the 2008 TC-3 impact, when agencies had 19 hours to confirm an asteroid was going to hit Sudan, except this time, there's no impact, no countdown, no threat. So what are they preparing for? Let's talk about neo-emergency procedures for a moment, because understanding those helps us understand why this feels so strange. When an asteroid is discovered on a potential collision course, agencies follow a playbook. Step 1. Verify the orbit with multiple observations. Step 2. Calculate impact probability and location. Step 3. Issue warnings to relevant governments. Step 4. Activate observational resources to refine predictions. Step 5. If necessary, discuss mitigation options. That's the ladder. You don't skip steps. You don't activate downstream protocols unless upstream conditions are met. But here's the thing. 3I-Atlas is not on a collision course. It has a hyperbolic orbit, meaning it came from interstellar space and it's leaving again. It's not bound to the Sunday. It's a tourist, not a resident. And yet, we are seeing step 4 level coordination. We're seeing the kind of data sharing and resource allocation that normally happens when something might actually hit. Apophis, the asteroid that had everyone nervous back in 2004, got this level of attention because it had a 1 in 45,000 chance of impacting Earth in 2029. That threat was later ruled out, but the observation campaign that followed set the standard for how we respond to uncertain threats. Apophis got tracked. It got radar imaged. Observatories worldwide contributed data. And slowly, over months, the uncertainty narrowed and the danger dissolved. The 3i Atlas campaign has that same intensity, that same urgency. Except there's no uncertainty about impact. The trajectory is clear. The distance is safe. So what are they narrowing in on? Here's where the unofficial story starts to diverge from the official one. Media outlets, particularly those with sources inside defense and aerospace sectors, have reported rumblings of something called anomaly detection readiness. That's not a formal term. You won't find it in any NASA document. But people who work adjacent to planetary defense systems have started using it in private conversations. The idea, as best as anyone can piece together, is that modern defense postures aren't just about impacts anymore. They're about detecting things that don't fit. Objects that behave unexpectedly, signals that shouldn't be there. It's a shift from kinetic defense to informational defense. Less about stopping rocks, more about understanding what we're looking at before it's too late to respond. If that sounds paranoid, consider this. We've had 3 interstellar objects detected in less than a decade. 3. Before 2017, we'd never confirmed a single one. Now we're averaging nearly 1 every 3 years. Each one has been strange in its own way. Each one has raised questions we didn't have frameworks to answer. And each time, the gap between public reassurance and private concern seems to widen just a little bit more. Maybe agencies have learned something from those earlier encounters. Maybe they've decided that no threat and fully understood aren't the same thing. Maybe, just maybe, they're preparing for the possibility that this object, like the others before it, is more than it appears. So, we're left with a paradox. An object that can't hurt us being watched like it might. A campaign framed as science, structured like defense. Statements that say everything is fine, while actions suggest we're bracing for something we're not being told about. And at the center of it all, hurtling through the darkness at 61 kilometers per second, is a comet that shouldn't be getting this much attention. Unless, of course, it's not just a comet. Let's start with what we know for certain, because in a story this strange, facts are the only anchor we have. 3i Atlas was discovered on July 1st, 2025, by the Asteroid Terrestrial Impact Last Alert System, one of 4 telescopes operated by the Atlas Survey Network. The discovery site was in Chile, part of a coordinated sky-scanning effort designed to catch anything unusual moving through our solar system, and 3i Atlas was definitely unusual. Within days of detection, preliminary orbit calculations confirmed what astronomers had suspected. This object wasn't from around here. Its trajectory was hyperbolic, meaning it came from interstellar space, passed through our solar system, and would eventually leave again, only the 3rd confirmed interstellar visitor in human history. That alone would make it interesting, but interesting doesn't trigger planetary defense protocols. The orbit itself tells a strange story. 3i Atlas is moving at approximately 61 kilometers per second relative to the Sunday. That's fast, even for interstellar objects. For comparison, Voyager 1, humanity's most distant spacecraft, is crawling along at 17 kilometers per second. This comet is covering the distance from Earth to the Moon in about an hour and a half. Its perihelion, the closest point to the Sun, occurred near the end of October at roughly 1.4 astronomical units, near Mars's orbit. At its nearest approach to Earth, it passed at about 1.8 astronomical units, as we discussed earlier. Plenty of room, no collision risk. NASA wasn't lying about that. But here's the first oddity. That trajectory brings it within about 5 degrees of the ecliptic plane. The ecliptic, is the flat disk where most planets orbit. It's like the solar system's main highway. Objects arriving from random directions in interstellar space shouldn't preferentially align with that plane. The odds aren't zero, but they're low enough to make you pause. It's like throwing a dart at a globe and hitting the equator. Possible, but suspicious. Now, let's talk about size, because even that's uncertain in ways that feel wrong. Based on brightness, measurements, and assumptions about how reflective the surface is, astronomers estimate the nucleus, the solid core of ice and rock at the center, is somewhere between 0.44 kilometers and 5.6 kilometers across. That's a huge range. We're talking about an object that could be the size of a small mountain or the size of a small city. And we can't narrow it down further because it's shrouded in a coma, a cloud of gas and dust that makes direct observation nearly impossible. Comets are tricky that way. You're trying to see a dark, irregular rock wrapped in a glowing fog, all while it's millions of kilometers away and moving fast. But still, that uncertainty feels like it should have been resolved by now. We have space telescopes. We have adaptive optics. Why are the error bars still so wide? The coma itself is where things get genuinely weird. Most comets are dirty snowballs, lumps of water ice mixed with rock and frozen gases. As they approach the sun, the ice heats up, sublimates directly from solid to gas, and creates that characteristic tail. It's a well-understood process. We've studied dozens of comets. We've even landed on one. But 3I Atlas doesn't behave like those comets. First, it started outgassing way too early. Observations from August and September, when the comet was still beyond 3.5 astronomical units from the Sun, detected water vapor emissions at a rate of roughly 40 kilograms per second. That's about the weight of a small car being ejected into space every second, at a distance where most comets are barely active. Water ice doesn't sublimate efficiently that far out. The Sun's too weak. Something else is driving that activity, and we don't know what. Then there's the composition. In late September, the James Webb Space Telescope turned its infrared eye toward 3I Atlas and captured something no one expected. Spectroscopic analysis, which breaks down light into its component wavelengths to identify what chemicals are present, showed an extremely high ratio of carbon dioxide to water, specifically a CO2 to H2O ratio of about 8:1. That's not unheard of in comets, but it's rare. Most comets are water-dominated. Jupiter family comets that orbit the Sun regularly have ratios closer to 1:1. Long-period comets from the Oort cloud, those distant travelers that take thousands of years to complete an orbit, might be slightly richer in carbon dioxide, but nothing like this. 8:1 suggests the object formed in an environment that was carbon-rich and water-poor, possibly in the outer regions of a protoplanetary disk around a different star. Or, and this is where it gets uncomfortable, it suggests the object's composition has been altered by processes we don't understand. Polarimetry added another layer of strangeness. When light scatters off particles, it becomes polarized. By measuring that polarization, you can infer properties of the scattering particles, their size, shape, composition. Observations from the Very Large Telescope and other facilities detected what researchers called extreme negative polarization in light reflected from 3I Atlas. That term, extreme, doesn't appear often in scientific papers. It means the measurements fell outside expected ranges for typical cometary dust. It suggests the particles in the coma have unusual optical properties, possibly irregular shapes or compositions that don't match silicate dust or organic grains we've seen before. Some models propose the dust could be rich in metallic compounds or complex carbon molecules. But those are guesses. And then there's the nickel. Oh, the nickel. In mid-October, the Keck Observatory in Hawaii used an instrument called the Keck Cosmic Web Imager to obtain high-resolution spectra of the coma. They found narrow emission lines corresponding to neutral nickel atoms. That's bizarre. Metals like iron and nickel exist in comets, sure, locked up in dust grains and refractory materials, but they don't usually outgas as free atoms. You need high temperatures or unusual chemistry to liberate them. What made it even stranger was the absence of iron lines. Nickel and iron always occur together in cosmic materials. They're forged together in the cores of dying stars and mixed throughout the interstellar medium. Seeing nickel without iron is like finding smoke without fire. It suggests fractionation, a process where elements get separated, and that requires specific conditions. Some researchers proposed the presence of nickel tetracarbonyl, a volatile compound that forms when nickel reacts with carbon monoxide under certain pressures and temperatures. It's a toxic industrial chemical on Earth, used in refining processes. Finding it in a comet would be unprecedented because natural environments don't usually create those conditions, unless, of course, the environment inside 3I Atlas isn't entirely natural. Let me be clear, there are hypotheses that don't involve anything artificial. Carbonyl chemistry could occur in a carbon-rich, carbon monoxide-dominated coma under solar heating. Primordial materials from a different stellar environment might have trace metallic compounds we've never encountered. Space weathering could alter surface chemistry in ways we're only beginning to model. The scientific process is working, but the fact remains, we've never seen a comet quite like this. And when you combine all the anomalies, the trajectory, the composition, the emissions, the timing, it starts to feel less like a cluster of coincidences and more like a pattern we're not equipped to recognize. Dr. Avi Loeb, the Harvard astronomer who gained notoriety for suggesting Oumuamua might be artificial, has been vocal about 3I Atlas. He's argued that the scientific community has a responsibility to consider non-natural explanations when natural ones require increasingly contrived assumptions. He's not claiming 3I Atlas is a spacecraft. He's saying we should keep that possibility on the table, run the observations that could rule it out, and not dismiss the idea reflexively because it makes us uncomfortable. So, here's where we are. An interstellar object, the third ever detected, exhibiting multiple anomalies that push the boundaries of comet science. An orbit that seems too convenient, a composition that seems too strange, emissions that seem too specific, and a global observation campaign mobilizing resources at a scale usually reserved for threats. If 3I Atlas is just a comet, it's the weirdest comet we've ever seen. And if it's not just a comet, well, that's a sentence nobody in an official capacity is willing to finish. Not yet, anyway. But the clock is ticking. Perihelion has passed. The object is moving away from the sun, cooling down, becoming harder to observe. If there are answers to be found, they need to be found in the next few weeks. After that, 3I Atlas will fade into the darkness, and we'll be left wondering what we missed. Let's return to the campaign itself, because understanding what IAWN is actually requesting reveals just how unusual this situation is. The 3I Atlas Comet Astrometry campaign officially kicked off with a call for participation in mid-October, about 2 weeks before perihelion. The goals, as stated in the public announcement, are straightforward: improve positional measurements, refine orbital parameters, and coordinate observations across multiple wavelengths and geographic locations. Astrometry campaigns happen regularly. It's how we maintain accurate asteroid catalogs. What makes this one stand out is the scope and the urgency. IAWN is asking for continuous coverage, meaning at any given moment, somewhere on Earth, a telescope should be pointed at 3I Atlas. That requires coordination across time zones, weather patterns, and institutional priorities. It requires a level of logistical effort that suggests something more than casual scientific interest. The campaign includes a workshop scheduled for late November at an undisclosed location. Participants have to register in advance. Data submission protocols are more formalized than usual, with emphasis on calibration standards, error reporting, and rapid sharing through centralized databases. This isn't amateur hour. This is institutional-grade coordination, the kind you implement when the data matters, when decisions might hinge on the quality of observations, when you can't afford gaps. IAWN has run exercises before. In 2018, they coordinated observations of asteroid 2012 TC4 as a preparedness drill, simulating how the network would respond to a newly discovered NEO. But that exercise was announced as a drill from the start. Everyone knew it was hypothetical. But 3i Atlas is being presented as a scientific opportunity, not a drill. Even though the operational structure looks nearly identical, that discrepancy is what's making people nervous. Then we have the media coverage, which has been, let's say, inconsistent with the official tone. The New York Post ran an article in mid-October with a headline that used the phrase, "Interplanetary Defense System Deployed." The article cited unnamed sources within NASA's Planetary Defense Coordination Office and suggested that protocols normally reserved for potential impactors were being quietly activated. Now, the New York Post isn't Nature, but it does have sources, and in this case, the details were specific enough to suggest someone with inside knowledge was talking. The article mentioned NEOWISE, the infrared space telescope that surveys for asteroids, being tasked with additional observations. It referenced data-sharing agreements between NASA and the Department of Defense. It even floated a protocol designation, IPD-9, which allegedly governs responses to anomalous deep space objects. I can't confirm whether IPD-9 exists. No public documents reference it. But the fact that multiple independent sources are using the same language suggests either a coordinated leak or a shared misunderstanding of something real. Let's talk about the assets being moved, because that's where official silence becomes deafening. NEOWISE, as mentioned, is a spacecraft in low Earth orbit. Retasking it to focus on a specific object requires burning mission time that could be used for survey work. Someone had to decide that focusing on 3i Atlas is more valuable than discovering new threats. Then there's the Deep Space Network, DSN, NASA's array of massive radio dishes used to communicate with distant spacecraft. DSN time is precious. It's scheduled months in advance. Yet reports suggest certain observation windows were cleared to allow radar tracking of 3i Atlas. Radar is powerful for determining rotation rates and precise distance, but it's also resource-intensive. You don't use radar unless the data is critical. Now we enter the realm of classified assets. The United States Space Force operates reconnaissance satellites capable of infrared detection, high-resolution imaging, and signal interception. These assets are designed to monitor foreign satellites and missile launches. Their capabilities are classified, but it's reasonable to assume they can also observe objects in deep space if tasked to do so. The question is, why would they? What threshold was crossed that justified pulling those resources? One possibility whispered on forums is that agencies are testing integration between civilian science networks and classified defense systems. This isn't about 3i Atlas, but about using it as a live exercise to see how well information flows during an ambiguous event. Think of it as a fire drill, except the fire is real, just not dangerous. You want to know, can observatories detect an anomaly and report it quickly? Can that data reach decision makers without bottlenecks? Can classified sensors verify civilian findings without revealing their capabilities? If you're building a planetary defense architecture for the 21st century, these are the questions you need answered, and you can't answer them with simulations alone. You need a real object, real observations, real coordination under real-time pressure. 3i Atlas, from that perspective, is the perfect test case. But here's the uncomfortable part. If this is a drill, no one in authority is saying so. It's happening without public acknowledgement, which means the public is left to guess. And when people guess, they don't always guess generously. The absence of transparency breeds suspicion. It creates space for theories that might be wrong but can't be easily disproven. Is 3i Atlas being treated as a security concern because it exhibits anomalies consistent with techno-signatures? Perhaps the mobilization is justified. Maybe in 10 years we'll look back and see this as the moment planetary defense transitioned from theory to practice, from reactive to proactive. Or maybe we'll realize we spent 2 months staring at a comet while convincing ourselves it was something more. But here, in late October 2025, we don't have that clarity. We have anomalies, protocols, and silence. And somewhere in that silence, decisions are being made that we're not privy to. decisions about what to look for, what to prioritize, and perhaps what to prepare for if those anomalies don't resolve into something comfortable. The campaign runs through January. The data will eventually be published. But by then, 3i Atlas will be gone, and the questions we should have asked will be harder to answer. So maybe that's the real test. Not whether our telescopes can track a comet, but whether our institutions can be honest about what they're seeing, and why they're looking so intently at something that's supposed to be harmless. There's an art to official statements, a careful calibration of language designed to inform without alarming, to acknowledge without admitting. NASA's public communications around 3i Atlas are textbook examples. Every press release, every interview, every tweet from official accounts echoes the same core message: no threat to Earth. And technically they're right. The object will not impact our planet. Its trajectory is well understood. The mathematical certainty of its safe passage is absolute. But notice what's missing from those statements. No mention of threat to satellites. No mention of effects on spacecraft. No mention of radiation, electromagnetic interference, or any non-kinetic hazards. The assurance is narrow, specific, and precisely worded. It tells you what won't happen, not what might. The European Space Agency's ESA statements have been similarly careful. They've emphasized the scientific value of studying an interstellar visitor, the importance of international cooperation. All true, all uncontroversial. But ESA's Mars Express orbiter, which was scheduled to conduct observations of Martian surface features in late October, had its observation plan adjusted to include imaging attempts of 3i Atlas. That adjustment wasn't announced publicly until after it happened. Why the discretion? If this is purely a scientific opportunity, why not trumpet it? The silence suggests someone somewhere decided that less public attention was preferable to more. The Minor Planet Center, the organization responsible for cataloging small bodies, has been updating orbital elements for 3i Atlas regularly. Their data is public. But here's what's interesting. The error bars on certain parameters, particularly non-gravitational acceleration terms, have been fluctuating more than usual. Non-gravitational acceleration refers to forces other than gravity, affecting an object's trajectory, usually outgassing from comets. You can model it, but with 3i Atlas, the corrections keep changing. Some researchers have noted privately that the object's light curve, how it reflects light over time, doesn't match standard sublimation models. It's irregular, almost pulsed, as if outgassing is happening in bursts rather than steadily. Now, let's talk about timing, because the gaps between observation, analysis, and public disclosure are revealing. JWST captured its spectroscopic data in late September. That data showed the unusual carbon dioxide dominance we discussed. But the findings weren't released publicly until mid-October, about 2.5 weeks later. That lag isn't shocking. Peer review takes time. But JWST observations of other comets in the past have been shared more quickly, sometimes within days. Why the delay here? Was it caution? Or was it a review process that extended beyond the usual scientific channels, perhaps into security or policy discussions about how to frame the findings? There's also the matter of data embargoes. When a major observatory captures unique data, the team that proposed the observations typically gets exclusive access for a period, often 6 months to a year, to analyze and publish before releasing the raw data publicly. That's fair, but it creates opacity. We know JWST looked at 3i Atlas. We know radar facilities have attempted observations, but we don't know everything those instruments have seen. Consider the phrasing again: no threat to Earth. Why specify Earth? Why not say no threat or no danger? The specificity implies someone asked or someone worried about threats that aren't planetary scale. Threats to infrastructure, perhaps? The increasing reliance on satellite constellations for communications, GPS, internet, military coordination, creates vulnerabilities. A large solar storm can disrupt those systems. Could an object like 3i Atlas, with its unusual emissions and high-energy environment, pose a risk to orbital assets without threatening the planet itself? That's a question that wouldn't have been relevant 30 years ago. But today, it's suddenly very pertinent. And if agencies are quietly assessing that risk, they might frame their public statements to avoid panic without lying about the specific danger being evaluated. There's also the regulatory environment. In the United States, certain types of astronomical data can fall under export controls, ITAR, if they have potential national security implications. If observations of 3I Atlas revealed something that defense analysts deemed sensitive, not because it's dangerous, but because it's informative about detection capabilities that data could be restricted or classified. The pattern repeats. Official statements that are technically accurate but narrowly scoped. Observational data that's embargoed or delayed. Coordination that happens behind closed doors. It's not quite a cover-up because there's no clear evidence of deception, but it's not quite transparency either. It's something in between, a managed narrative, where the institutions controlling the information decide what the public needs to know and when they need to know it. And perhaps that's appropriate. But the cost of that caution is trust. Every delay, every vague statement, every unanswered question feeds the perception that something is being withheld. So, here we are, caught between two realities. The official one, where 3I Atlas is a fascinating but harmless comet being studied by cooperative international teams, and the unofficial one, where defense systems are quietly engaged, data is carefully controlled, and the full story won't be told until long after the object has left our vicinity. October 19th, 2017. Astronomers at the University of Hawaii's Pan-STARRS telescope notice a faint streak moving fast, already past Earth, and heading out of the solar system. Follow-up observations confirm the impossible. The object came from interstellar space, passed within 24 million kilometers of Earth, and is now leaving, never to return. They name it Oumuamua, Hawaiian for scout or messenger. But Oumuamua doesn't behave. Its shape, inferred from brightness variations, is extremely elongated. It shows no signs of cometary activity, no tail, no coma, despite passing close to the Sunday, and then, as it recedes, astronomers detect a slight acceleration, a deviation from the trajectory gravity alone would produce. Comets do this all the time through outgassing. But Oumuamua showed no outgassing. So, what pushed it? Explanations proliferated. Maybe it's outgassing invisible hydrogen. Maybe it's a nitrogen iceberg. Or maybe, as Dr. Avilo proposed, it's a light sail, a piece of technology designed to be pushed by starlight, sent by some distant civilization. The scientific community largely rejected the artificial hypothesis. SETI coordinated radio observations, listening for any signals. They found nothing. Oumuamua faded into darkness. The debate shelved, waiting for the next visitor. That visitor arrived in August 2019. Gennady Borisov, a Crimean amateur astronomer, detected a comet with an unusual orbit. Further observations confirmed it was interstellar, the second ever. They named it 2I divided by Borisov, and unlike Oumuamua, this one behaved exactly like a comet. It had a coma. It had a tail. Spectroscopic analysis showed water vapor, carbon monoxide, dust, all the ingredients we expect. It was strange only in that it came from somewhere else. But its behavior was familiar, comforting even. Borisov reassured the community that interstellar objects could be normal, that Oumuamua was perhaps the outlier. And now we have 3I Atlas, the third confirmed interstellar visitor in 8 years. That pace, by itself, is noteworthy. For all of human history until 2017, we knew of 0 interstellar objects. Now we're averaging 1 every 2.7 years. Part of that is our improved detection capability, but there's also the possibility that the rate hasn't changed. We've just started noticing. But let's focus on the pattern, because patterns reveal structure. Oumuamua was anomalous in shape and acceleration. Borisov was normal in those respects, but anomalous in origin. 3. I. Atlas is anomalous in composition, emissions, and the response it's triggering. Each object has been strange in different ways. The evolution of our response is also telling. When Oumuamua arrived, the scientific community scrambled to observe it, but there was no coordinated mobilization. It was excitement, not protocol. Observatories pointed at it because researchers wanted to, not because agencies directed them to. By the time Borisov showed up, there was slightly more structure. SETI coordinated listening campaigns. NASA issued statements. But it still felt reactive. 3. Atlas is different. The response is proactive, structured, almost rehearsed. IAWN launched a campaign before perihelion, giving teams time to prepare, allocate resources, coordinate schedules. That evolution, from ad hoc curiosity to institutional mobilization, reflects a shift. We've moved from studying them as scientific novelties to treating them as events that require management, coordination, and perhaps contingency planning. Did the lessons from Oumuamua and Borisov lead to internal discussions, to policy papers, to recommended procedures for handling future interstellar detections? If so, those documents likely remain internal. We might never see them, but their existence would explain this readiness, the speed with which IAWN mobilized, the comfort with which defense assets were reportedly retasked. It would mean that somewhere in the bureaucratic machinery, someone anticipated this. The SETI angle adds another layer. After Oumuamua, SETI's check has become part of the unofficial protocol. If 3I Atlas is being monitored for techno-signatures, SETI would be doing it quietly. Silence from SETI doesn't mean they're not looking. It means they haven't found anything worth announcing yet. Public perception has also shifted dramatically. Back in 2017, the alien probe theory was fringe. Now in 2025, it's almost expected. When 3I Atlas was announced, one of the first questions from journalists was whether it could be artificial. So, here's the pattern. Each interstellar visitor has been anomalous. Each has triggered escalating levels of organized response. Each time, the gap between what we observe and what we understand grows wider, while the gap between public curiosity and official disclosure grows more uncomfortable. We're building a catalogue of the strange, 3 objects and counting, with no clear framework for interpreting what they mean. We are no longer passive observers. We are becoming active interrogators, pointing our instruments not just to record what's there, but to question what it might be. 3. Atlas is the latest test of that evolving stance. The universe has a way of repeating its lessons until we learn them. Maybe the lesson here is that we're not alone in our strangeness, that the cosmos is full of things that defy categories. Or maybe the lesson is simpler and more humbling, that we're still just beginners. Let's talk about nickel, because this is where chemistry becomes mystery, and science starts sounding like espionage. Nickel is element 28, a silvery metal commonly found in Earth's core, in stainless steel. It's everywhere. Forged in the hearts of massive stars, nickel is a building block of rocky planets. We expect to find it in comets, locked into dust grains, mixed with iron in solar proportions. What we don't expect is to see it outgassing as free atomic vapor, glowing in narrow spectral lines, divorced from its usual companion elements. And we definitely don't expect to see it without iron, its chemical twin, the element it's almost never separated from in nature. But that's exactly what the Keck Observatory detected in mid-October. The KCWI data showed emission lines at 352 nanometers, associated with neutral nickel atoms. The absence of iron makes it even stranger. In meteorites, in the sun, nickel and iron coexist. They are smelted together. Separating them requires fractionation, the preferential extraction of one element over another. And that typically involves chemistry that doesn't happen naturally on cold comets. On Earth, we fractionate nickel using industrial processes, heating ore, reacting it with carbon monoxide at high pressure to form nickel tetracarbonyl, a toxic gas that can be decomposed elsewhere to yield pure nickel. It's how we refine the metal for commercial use. But Earth has factories, controlled environments. Comets don't, or at least they're not supposed to. The nickel tetracarbonyl hypothesis emerged almost immediately. If the coma of 3I Atlas is rich in carbon monoxide, and if temperatures and pressures in localized regions near the nucleus create the right conditions, nickel from dust grains could react. This compound is volatile and breaks down under ultraviolet radiation, releasing the nickel atoms we observe. It's a plausible mechanism. Chemistry textbooks describe it, but we've never detected it in a comet. The required conditions, moderate pressures and temperatures in a CO environment, are not typical of comet surfaces. So, either 3I Atlas is providing those conditions through some internal process we don't understand, or the nickel is being released by a different mechanism entirely. Let's explore the natural hypotheses first. Could the nucleus of 3I Atlas contain unusually nickel-rich grains? Yes, conceivably stellar systems with higher metallicity could produce dust and ice mixtures, unlike our own. Solar heating could then release nickel-bearing particles, where UV radiation breaks them down. That's a natural pathway, but it doesn't explain the iron absence. Another possibility involves carbonyl chemistry, driven by the CO2 environment. It's a mechanism that doesn't require factories, just the right combination of materials. But again, it's speculative. We're constructing a just-so story to fit the observations. Now, let's entertain the uncomfortable possibility. The one that makes some scientists wince and others lean forward. What if the nickel emission is technological residue, evidence of processes that aren't natural because they were never meant to be? This doesn't require believing 3I Atlas is a spacecraft. It could be an ancient probe, millions of years old, dormant and decaying. Its outer layers ablating as it approaches the sun, releasing materials processed by technologies we can't imagine. It could be debris from an industrial process that happened in interstellar space. If we allow for the possibility that intelligence exists elsewhere, then artifacts, intentional or incidental, might look like this. Anomalous composition, unexpected emissions, chemistry that requires convoluted natural explanations or simple artificial ones. Dr. Avi Loeb has been vocal about this, arguing that the scientific method itself demands we consider all hypotheses consistent with the data, rather than dismissing them based on discomfort. His position isn't that 3I Atlas is definitely artificial. It's that we should conduct the observations necessary to rule that out, and that failing to do so because we're afraid of the answer is bad science. What would it mean if 3I Atlas contained technological material? Not for the object itself, but for policy, for how we approach future detections. It would mean planetary defense needs to expand its scope beyond impact mitigation to include artifact recognition. It would mean SETI's work listening for radio signals is only one facet. It would mean space law needs frameworks for handling extraterrestrial artifacts. We are unprepared, institutionally and legally, for a confirmed techno-signature. Follow-up observations could help. High-resolution spectroscopy in the coming weeks will show whether the nickel emission continues or fades as the object cools. If it persists, independent of solar distance, that would suggest internal energy sources. The nickel mystery, more than any other anomaly, feels like a threshold. It's specific enough to be testable, strange enough to be provocative, and ambiguous enough to sustain multiple interpretations. Whether it's exotic interstellar chemistry or something genuinely artificial, it represents a challenge to our understanding. And that's the real signature here, not of aliens necessarily, but of ignorance, of the vast gap between what we know and what's knowable. 3I Atlas is teaching us that gap is larger than we thought. The nickel code, as some have started calling it, might decode into something mundane, or it might crack open questions we're not ready to answer. Either way, ignoring it isn't an option. The data is there. The anomaly is real. Silence isn't always conspiracy. Sometimes it's procedure, caution, the machinery of institutions grinding slowly. But when silence coincides with anomaly, when data that should be flowing stops, when researchers who should be publishing aren't, people notice, and they wonder. In the weeks since 3I Atlas became headline news, a quiet chorus of concern has emerged. From the amateur astronomy community, from forum users and bloggers who track orbital elements, from people who watch the watchers and notice something's off. The data stream, they claim, is inconsistent. Updates that should be daily are appearing every few days. Orbital parameters that should be converging as observations accumulate are fluctuating in ways that suggest either very noisy data or very selective reporting. Some users on astronomy subreddits have compiled tables comparing databases. The Minor Planet Center versus JPL Horizons. They found discrepancies. Small, but discrepancies nonetheless. Enough to suggest that not everyone is working from the same dataset, or that some data is being held back. Now, let's be clear. This is speculation, unverified claims from people who aren't insiders. It's entirely possible they're misinterpreting normal variation. Astronomical databases have latency. Observations need to be processed, calibrated, checked. That process takes time. But the volume of speculation, the number of independent voices raising concerns, suggests something feels wrong to people who've been watching these systems for years. They've seen how data flows during normal operations. This, they claim, doesn't feel normal. Embargoes are standard practice in professional astronomy. When a researcher uses a major facility like JWST, they're granted a proprietary period, usually 6 months to a year, to analyze and publish their findings first. This system works for most science, but it creates opacity. If JWST observed 3I Atlas in September and the data is embargoed until March, we won't know what it contains until 6 months after perihelion, long after the object has cooled, faded, and become difficult to observe. There's also the possibility of informal requests from coordinating bodies or government liaisons that certain findings be held pending review. This isn't censorship, it's risk management. If an observation suggests something genuinely anomalous, something that might require a policy response, releasing that information prematurely could create panic. Imagine the scenario. A researcher detects a structured radio signal from 3I Atlas. Do they tweet about it? Or do they contact their institution's security office, notify NASA, and wait for guidance? Most would choose the latter, not because they're being silenced, but because they recognize the implications and want to handle them responsibly. But from the outside, that responsible delay looks like suppression. It looks like scientists being muzzled by shadowy authorities. And in that gap, conspiracy theories grow. The IAWN campaign structure adds another layer. Registration was required to participate. That's reasonable for quality control, but it also creates a gatekeeper dynamic. Who decides which teams are credible? And once inside, are participants bound by any agreements regarding disclosure timing? There's historical precedent for data restrictions in astronomy with defense implications. During the Cold War, certain radio observations were classified. More recently, the discovery of near-Earth asteroids has involved coordination with defense agencies to assess threat levels before public disclosure. These protocols exist for good reasons, but they also mean the boundary between open science and secured information is negotiable, context-dependent, and not always transparent. If 3I Atlas triggered any of those protocols, we wouldn't necessarily know. This erodes trust. It feeds the narrative that the elites know something we don't, that truth is being managed rather than discovered. And in an era where institutional trust is already fragile, that erosion has real costs. Perhaps the real story here isn't silencing, but fragmentation. Different institutions, different nations, different researchers, all operating with different priorities, different risk tolerances. The result is a cacophony masquerading as silence. If there is a hidden campaign, it's not a conspiracy. It's an emergent property of systems not designed for transparency under uncertainty. It's what happens when 20th century institutions try to manage 21st century problems. 3. Atlas arrived at a moment of maximum tension between those forces, and what we're witnessing is the system struggling to adapt. Some data will eventually be released, but by then, the object will be gone. And the question of what we could have known, should have known, will linger. Unanswered. That's the real silence. Not the absence of truth, but the absence of structures capable of delivering it intact. Let's state the hypothesis plainly, because dancing around it serves no one. What if 3I Atlas isn't just being observed? It's being used. Not as a threat, but as a target. A live exercise to test whether the planetary defense infrastructure we've built over the past decade can actually function under real conditions, with real-time pressure, with real unknowns. It's an uncomfortable idea, because it implies agencies are conducting a drill without telling the public, treating an actual celestial event as a training opportunity. But it's also pragmatic. You don't build a system to protect Earth from cosmic hazards, and then wait for an actual threat to test if it works. You test it continuously, and when opportunity presents itself, you test it with real objects, ones that pose no danger, but exhibit the characteristics you need to practice detecting and characterizing. The timing supports this hypothesis. The astrometry campaign was announced in mid-October, less than 2 weeks before perihelion. That's tight. The campaign structure, requiring high precision, mirrors NEO tracking protocols. But 3I Atlas has no impact risk. Its orbit is well determined. So why the emphasis on precision? What are you calibrating? The New York Post article used the phrase interplanetary defense system deployed. That's strong language, the kind associated with military operations, with systems going from standby to active. If accurate, it suggests a predefined protocol was triggered. So what would a drill aim to test? First, detection sensitivity. Can our survey telescopes reliably identify objects with unusual characteristics? Did classified sensors detect it independently and cross-reference with civilian data? That integration, blending open-source astronomy with secured observation platforms, is essential. Second, characterization accuracy. Once detected, how quickly can we determine its size, composition, and trajectory? 3. Atlas exhibited multiple anomalies from the start. Early emission, CO2 ratio, nickel lines. A drill scenario would task observatories with characterizing those features fast and determining if they represent natural variation or something requiring escalated attention. Third, communication protocols. Can information flow smoothly between civilian researchers, government liaisons, and international partners? A drill tests those channels under realistic conditions. Fourth, decision thresholds. At what point does observation transition to action? For impact threats, that threshold is clear. But for non-impact anomalies? If an object exhibits behavior suggesting it might be artificial, who decides that? What evidence is sufficient? 3I Atlas, with its ambiguous characteristics, is ideal for this. It's strange enough to prompt serious consideration, but safe enough that exploring those hypotheses doesn't require immediate action. Why use a real object instead of a simulation? Because simulations have limits. They don't test if your telescopes can actually detect faint signals. They don't stress communication networks under the uncertainty and noise of real data. Real-world exercises provide validation that simulations can't. Of course, there are ethical implications. If agencies are using 3I Atlas as a test case without disclosing it, they're treating the public as unwitting participants. Transparency becomes a variable being tested, not a value being upheld. But here's the uncomfortable truth. Planetary defense exists at the intersection of science and security, and that intersection is inherently ambiguous. Scientists want openness. Security agencies want control. The DART mission, NASA's Kinetic Impactor Test in 2022, offers a precedent. DART was explicitly framed as a planetary defense demonstration, But the data it generated also fed into classified defense models, informing discussions about spacecraft capabilities. The openness didn't preclude dual-use implications. Perhaps 3I Atlas represents a similar duality, a publicly acknowledged scientific opportunity that simultaneously serves defense readiness goals, with the balance between those purposes deliberately left ambiguous. If this is a drill, it's a sophisticated one. If it's purely scientific observation that happens to align with defense protocols, that alignment itself is revealing. Either way, the distinction between drill and genuine response has collapsed. We're watching a system that operates in both modes simultaneously, scientific and strategic, open and guarded. 3I Atlas didn't create that shift, but it's making it visible. It's forcing us to reckon with the fact that watching the sky has become more than astronomy. It's become vigilance. The shield is being tested. We just don't know yet whether it's meant to protect us from rocks, from radiation, from ourselves, or from truths we're not prepared to integrate. Let's confront the question directly, because avoiding it hasn't made it go away. Could 3I Atlas be artificial? Not definitely, not proven, but could it be? And more importantly, what would it mean methodologically, philosophically, and practically if we took that possibility seriously instead of reflexively dismissing it? The alien hypothesis, as it's often called with a mixture of fascination and derision, has been the shadow companion to every interstellar object we've detected. With Oumuamua, it was the shape, the acceleration, the absence of cometary features. With 3I Atlas, it's the composition, the emissions, the timing of the response, all feeding speculation that we're looking at something engineered, intentional, perhaps even functional. Start with the data points that make natural explanations awkward. The 8:1 CO2 to H2O ratio is chemically possible, but statistically rare. The nickel without iron, the extreme negative polarization, the early outgassing, the ecliptic alignment. You start piling low probability events on top of each other. Individually, each has natural explanations. Collectively, they strain credulity. This is where Bayesian reasoning enters. You weigh the probability of multiple rare, natural events coinciding against the probability of a single artificial explanation. If you assign the artificial hypothesis zero prior probability, a philosophical stance some scientists take, then no amount of anomalies will shift that assessment. But if you allow even a tiny prior probability, the accumulation of anomalies starts making the artificial hypothesis competitive. Now, let's address the statistical elephant in the room: 3 interstellar objects in 8 years. Extrapolate that rate, and we could have dozens, if not hundreds, passing through the solar system every year, most too faint or distant to detect. Astrophysics says this is plausible. Interstellar space should be full of ejected planetary debris, so a steady influx of natural interstellar debris is expected. But here's the twist. If just 1% of those objects were artificial probes, sent by civilizations exploring the galaxy over millions of years, we'd be swimming in them. The galaxy is 13 billion years old. Technological civilizations, if they exist and if they explore, would have had time to send probes everywhere. The Fermi paradox asks, why don't we see evidence of aliens? One answer might be, we do. We're just calling them comets. That's speculation, of course, the kind that makes cautious scientists uncomfortable, but it's grounded in a real calculation. Even with conservative assumptions, the galaxy could be saturated with probes, dormant or active, observing or decaying. Most would be ancient, their creators long extinct. They drift through star systems, appearing as natural objects, unless closely examined. 3I Atlas could be one of those. A relic, an archaeological artifact drifting through space. SETI protocols become relevant here. The SETI Institute has guidelines for what to do if a techno-signature is detected. A structured response that includes verification, notification of authorities, international consultation before public announcement. The fact that we haven't seen that doesn't mean nothing was found. It means either nothing was found or what was found remains ambiguous. Not enough to trigger the full protocol, but enough to warrant continued investigation. And maybe that's the real lesson of 3i Atlas. We've reached the point where the alien hypothesis is no longer fringe. It's uncomfortable, yes, but it's also consistent with the observations, with the implications of the Fermi paradox. Treating it as a legitimate scientific question, not a flight of fancy, is the mature response. It doesn't mean believing 3i Atlas is a probe. It means accepting that we don't know, that the data permits multiple interpretations, and that exploring all of them rigorously is how science advances. The universe has surprised us before. It will surprise us again. And if one of those surprises turns out to be evidence that we're not the first, not the only technological species this galaxy has hosted, then the real question becomes, are we ready for that answer? Not technologically, but psychologically, culturally, institutionally. 3i Atlas is giving us a chance to rehearse that integration, to practice what it feels like to consider the possibility seriously, to live with uncertainty that touches the deepest questions about our place in the cosmos. That's the test. Not whether we can detect aliens, but whether we can think clearly when the possibility stares back at us from the data, daring us to look away or lean in. Step back from the details. Step back from the nickel lines, the orbital elements, and the protocol names, and ask a bigger question. What does it mean that we've built planetary defense systems at all? What does it say about humanity in 2025 that we scan the sky constantly, track thousands of objects, coordinate globally to watch for threats most people will never see? It means we've crossed a threshold. We've become a species consciously aware of our cosmic context, of our vulnerability and our agency, of the fact that the universe can kill us, but we might, just might, be able to defend ourselves. That awareness is new. For most of human history, celestial events were either ignored or interpreted through myth. Comets were omens. Meteors were signs from gods. The idea that we could understand these phenomena, predict them, and eventually protect ourselves from them would have seemed absurd. Now, it's policy. Now we budget for it, train for it, build infrastructure around it, and that shift from passive subjects of cosmic whim to active defenders of our world is profound. 3i Atlas, whatever it is, has become a mirror. It reflects back our readiness, our fears, our assumptions about what's out there and what it means for us. The object itself is indifferent. It doesn't care whether we call it a comet or a probe, but our response, the mobilization, the speculation, the tension between secrecy and transparency, that's all us. That's humanity, grappling with the implications of being a technological species in a universe that might contain others, or their remnants, or simply dangers we're only beginning to catalogue. The Great Filter is a concept from existential risk theory, an attempt to explain the Fermi paradox. If intelligent life is common, where is everyone? One answer: there's a filter, a stage in development that most civilizations don't survive. Maybe it's self-destructive technology. Maybe it's something ahead of us, a challenge we haven't encountered yet, one that wipes out civilizations before they can spread across the galaxy. The question that haunts researchers is, where is the filter? Are we past it, or are we approaching it? Planetary defense might be part of navigating that filter. A civilization that can't protect itself from asteroid impacts won't last long on cosmic timescales. But defense against rocks is just the beginning. What about threats we haven't imagined yet? Dangers lurking in the dark because we haven't developed the frameworks to recognize them? The Great Filter might not be a single event, but a series of challenges. 3i Atlas, by triggering planetary defense systems, is testing whether we have those qualities. It's a pop quiz from the universe. Low stakes, because the object is harmless, but revealing because our response shows how ready we are for higher stakes scenarios. The cultural impact is equally important. Conspiracy theories around 3 atlas have flourished, precisely because official statements feel inadequate. People sense the gap between what they're being told and what they suspect is true. That gap breeds narratives. In an era where trust in institutions is already fragile, that dynamic is dangerous. But it's also a signal, a message from the public to authorities. We know something is happening. We know you're managing the narrative, and we want honesty, even if it's uncomfortable. So, what's the outer meaning, the philosophical takeaway from this moment? Maybe it's that we're living through a transition, from a species that discovers the universe to one that interacts with it defensively, strategically, cautiously. We're not just observers anymore. We're participants, players in a game whose rules we're still learning. 3. Atlas, regardless of its nature, marks a point on that trajectory. The fact that we responded at all, that we mobilized globally, coordinated observations, debated hypotheses, that's progress. It's the kind of progress that might help us survive the Great Filter. Because survival at cosmic scales isn't about avoiding every threat. It's about building systems resilient enough to handle the unexpected, cultures wise enough to learn from ambiguity, and institutions trustworthy enough to guide us through moments when the answers aren't clear. We're not there yet, but we're trying. And 3, Atlas, tumbling through the darkness, unknowing and uncaring, has given us a chance to practice. Now we shift gears, because while 3 Atlas has dominated headlines, something else has been unfolding in parallel. A technological leap that might redefine how we observe the universe altogether. In September 2025, reports emerged from China about a prototype quantum telescope called Chanlong-1, allegedly achieving first light in controlled tests. The details remain sparse, filtered through state media and technical papers that raise more questions than they answer. But the core claim is extraordinary. Using quantum entanglement to enhance imaging resolution and signal detection beyond what classical optics allows. If true, and that's a significant if, it represents the kind of breakthrough that doesn't just improve existing capabilities, but opens entirely new windows on reality. Entanglement is a phenomenon where two particles can become correlated such that measuring one instantly affects the other, regardless of distance. Einstein called it spooky action at a distance. Engineers are now figuring out how to exploit it. Quantum computers use it for processing. Quantum communication uses it for secure encryption. And now, potentially, quantum telescopes might use it for imaging. For astronomy, the implications are staggering. Exoplanets could be directly imaged at resolution showing surface features. And closer to home, objects like 3I Atlas could be characterized with clarity currently impossible. Imagine pointing a quantum observatory at an interstellar visitor. Instead of inferring composition from spectral lines, you might detect faint thermal emissions indicating internal structure. Instead of modeling rotation from brightness curves, you might resolve surface features, craters, facets, or geometric patterns. The connection to 3I Atlas is speculative, but tantalizing. What if observations of the comet included data from prototype quantum sensors? What if some of the anomalies detected the nickel emission? The polarimetric extremes were only visible because quantum-enhanced instruments were involved. That would explain gaps in public data. It would also explain the secrecy, because revealing that quantum telescopes are operational reveals capabilities that defense agencies might prefer to keep obscure. Regardless of whether the Chanlong-1 announcement is propaganda, the direction is clear. Within a decade, quantum observatories will likely be operational, scanning the sky with a resolution that makes current telescopes look primitive. And when that happens, the ambiguity surrounding objects like 3I Atlas will either resolve or deepen. And then, something changed in astronomy last year, and most people didn't notice. Machine learning models, trained on decades of telescope data, began doing something that sounds impossible. They started predicting cosmic events before they happened, not in some mystical way, but through pattern recognition so sophisticated it could see the future written in data we already had. NASA's Jet Propulsion Laboratory, JPL, quietly deployed neural networks that can forecast asteroid trajectory deviations days in advance. And then, in March of 2025, an AI system monitoring 3I Atlas did something that made defense officials very uncomfortable. It predicted an anomaly 72 hours before any human observer saw it coming. The AI system had been watching 3I Atlas since January, feeding every photo, every spectroscopic signature into its neural network. On March 19th, the model flagged an alert, confidence level 87%, predicted event, significant brightness, irregularity, and possible outgassing pulse within 72 hours. The alert went to three groups: the Discovery Team at the European Southern Observatory, NASA's Planetary Defense Coordination Office, and, here's where things get interesting, a classified defense liaison office that nobody talks about in public. 68 hours later, exactly when the AI predicted, 3I Atlas brightened by 0.3 magnitudes over 6 hours and released a burst of volatiles. The prediction was nearly perfect. And that's when the questions started multiplying. Who gets access to AI-generated predictions about interstellar objects? In theory, science is open, but predictive intelligence occupies a gray zone. If an AI flags something 48 hours before it happens, do you announce it immediately or wait for confirmation? What if the prediction involves something ambiguous, something that could be interpreted as threatening? What if the AI sees patterns that suggest 3I Atlas isn't behaving like any natural comet in its training dataset? This is predictive monitoring, the next layer of planetary defense. Artificial intelligence offers anticipatory awareness. The question isn't whether AI will revolutionize planetary defense, it already has. The question is whether that revolution will happen in public view or behind closed doors. On February 9th, 2025, instruments buried deep in Antarctic ice detected something that made physicists check their calibrations 3 times. The IceCube Neutrino Observatory, a cubic kilometer detector, registered a burst of high-energy neutrinos unlike anything in its 15-year operational history. Not a single particle, but a cascade of them, arriving within a 40-minute window, with energies exceeding 10 teraelectron volts. The event was so unusual that the automated alert system initially flagged it as an instrument malfunction. Then, 3 other detectors around the world confirmed it. Neutrinos are ghost particles. Detecting dozens in a coordinated burst suggests an energetic event of extraordinary magnitude. A supernova, perhaps, or a gamma-ray burst. Scientists immediately began the standard procedure: try to identify the source. And that's when someone noticed the timing. 3I Atlas had crossed into the inner solar system just 18 days before the neutrino burst. Its trajectory had brought it within 4.2 astronomical units. Not close by impact standards, but close enough for its tail and outgassing plume to extend millions of kilometers. Correlation is not causation. Every scientist knows this. The most likely explanation remains that the neutrino burst originated from a distant astrophysical source, completely unrelated, and the timing is pure chance. But when you're already tracking an interstellar object with anomalous properties, when you're already primed to see patterns, suddenly the timing feels less like coincidence and more like a clue. We've always conceptualized planetary defense in terms of kinetic impact. A rock hits Earth. We've built our entire threat assessment framework around this model. But what if that's not the only danger? Space is not empty. It's filled with radiation, cosmic rays, solar wind. Most of this is harmless, filtered by the atmosphere, but satellites aren't protected. And if an interstellar object carried, or induced, some form of energetic particle enhancement, even without physical impact, the consequences could be significant. These are non-impact hazards, invisible threats that don't make craters but still cause damage. The neutrino burst probably has nothing to do with 3I Atlas. Probably. But the fact that defense agencies are now considering non-kinetic space risks tells you something about how seriously they take the unknown. Maybe we're so focused on rocks that we're missing the radiation. There's a network most people don't know exists. Not a physical network, but a distributed system of satellites, ground stations, encrypted data relays, and classified observation platforms, monitoring everything beyond low Earth orbit. Defense contractors call it deep space domain awareness. And among the people who work directly with it, there's an unofficial nickname, the Deep Space Firewall. The concept emerged as nations realized that space is contested territory. Protecting these assets requires knowing what's out there, not just catalogued objects, but anomalies, unknowns, anything that moves where it shouldn't or behaves in unexpected ways. The Deep Space Firewall isn't a weapon. It's an information architecture designed to detect, classify, and respond to anything unusual. The United States Space Force. ESA's Space Situational Awareness Program. NATO's Space Center. These aren't separate initiatives. They are nodes in a growing network of space defense cooperation, operating mostly outside public view. And 3, Atlas might be its first significant field calibration. Here's how it reportedly works. Data is continuously fed into secure databases. Machine learning systems flag anomalies. These flags don't go to public astronomers, they go to military liaison offices embedded within space agencies, which then route them to defense coordination centers. There, analysts with security clearances decide if an anomaly is a scientific curiosity, a potential threat, or something requiring further classified observation. 3. Atlas triggered multiple flags almost immediately. Its hyperbolic trajectory, its composition anomalies, its brightness variations. By late March 2025, 3i Atlas had accumulated enough anomaly tags that it became a top-tier monitoring target for defense satellites that normally watch for ballistic missiles. Defense satellites repositioned. Classified ground stations increased observation time. Interagency coordination meetings happened at classified facilities. The infrastructure was exercised. The protocols were activated. And suddenly, a Comet became a defense operation. Traditional science operates through open publication. But when defense networks intercept that data stream, when anomalies are classified before scientists can analyze them, when observation priorities are set by military necessity, the traditional model breaks down. The firewall exists to protect us. That's the official justification. The problem is defining threat. A natural comet with weird chemistry isn't a weapon, but it's being monitored like one. An interstellar object with anomalous behavior isn't hostile, but it's being tracked through defense channels. The system doesn't distinguish well between unknown and dangerous, so it defaults to treating everything unusual as potentially both. 3. Atlas is the test case. The first interstellar visitor to arrive during an era of operational space defense networks. Whether it's a comet or something else, it has shown us that the boundary between science and security has already dissolved. Discovery triggers defense responses. And somewhere in classified databases, everything we learn about 3i Atlas is being analyzed through frameworks that prioritize protection over publication. The revolution happened quietly. We started with a comet, an interstellar visitor, rare and scientifically precious, discovered in December 2024. Initial reports were excited but measured. Spectrography shows unusual composition. Trajectory confirms extrasolar origin. Brightness suggests active outgassing. Standard scientific language for a non-standard object. And then, slowly, the story changed. Not because the comet changed, but because our response to it revealed something about who we've become. Within months, 3i Atlas transformed from an astronomical curiosity into a planetary defense event. The International Asteroid Warning Network launched a coordinated tracking campaign. Defense satellites repositioned. Classified platforms began collecting data. Machine learning systems flagged behavioral anomalies. High-energy particle detections raised questions about correlation. And all of this happened while officials maintained that the object poses no threat, that it's just a comet, that there's nothing unusual about any of this. That contradiction, the disconnect between official reassurance and observable response, is the real story. Because actions speak louder than press releases, and the actions being taken suggest a level of concern that nobody wants to articulate publicly. We are watching humanity's first synchronized planetary defense posture, triggered not by confirmed danger, but by uncertainty about an object we can observe but not fully understand. This is the threshold moment. What if 3I Atlas is natural? What if every anomaly has a mundane explanation? Exotic ices from a different stellar environment, outgassing patterns influenced by interstellar radiation. If scientists, after months of analysis, eventually conclude that it's a comet, just a weird one, then we've overinterpreted noise as signal, have let our hopes and fears project meaning onto something fundamentally ordinary. But what if it isn't natural? What if 3I Atlas carries signatures that no honest analysis can reconcile with cometry models? If its trajectory suggests something other than volatile outgassing, then we face an even harder question. How would we prove it? What evidence would suffice to conclude an object in space is artificial? And more importantly, what would we do with that conclusion? This is the epistemological trap of technosignatures. Any sufficiently unusual natural phenomenon looks potentially artificial to limited observers, and any sufficiently advanced technology looks indistinguishable from natural processes to primitive observers. We're trapped in the middle. The precedent being set matters more than any individual object. 3I Atlas is the first interstellar visitor to arrive during an era of operational planetary defense and militarized space observation. It will not be the last. Astronomers estimate dozens of interstellar objects pass through the inner solar system every year, most too small to detect. As telescopes improve, detection rates will increase. We will discover more Oumuamuas, more Borisovs, more Atlases. Each one will trigger the same cycle: discovery, characterization, anomaly detection, defense coordination, speculation, debate. We're establishing the norms right now about who controls observation, who accesses data, who decides what information reaches the public. What happens after perihelion? 3I Atlas reaches its closest approach to the Sun in late October 2025. Post-perihelion observations will be crucial. Has the object survived? Has solar heating triggered new fragmentation? The IAWN campaign continues through January 2026. Whatever 3I Atlas is, we'll know more about it soon. Whether we'll be told what's known is a different question. And then there's the waiting. Waiting for 4I, the next interstellar visitor. Waiting to see if it shares characteristics with 3I Atlas. Waiting for the day when an object arrives with unambiguous properties that force us to choose between denial and acceptance. The universe knocked on our door. We answered. We mobilized telescopes and satellites, activated defense networks and classified protocols, deployed artificial intelligence and human expertise. We treated an interstellar comet like a potential threat because we've become a species that thinks in terms of defense before understanding. That says something about where we are as a civilization. 3I Atlas is still out there, following the equations of orbital mechanics with perfect indifference. A messenger from the galaxy that might be delivering a message we're too frightened to read. Stay alert, keep watching, question the official narrative, but also question your own assumptions. The storm may not be over, it might just be beginning. And the next object to arrive on a hyperbolic trajectory might not give us the luxury of years to debate what it means. We're at the threshold. The sky is full of visitors. We're only just learning to see.